So I want to talk about monitoring soil water quality using trace elements. So my main research interest is trace metals in the environment. And what I'll do is I'll compare some results from the Elmvale Groundwater Observatory, which I'll explain to you, with some data for monitoring wells in the same area. So I'll just give you a little bit of a background about trace metals and say a few words about water. And then I'll show you some of the results that we have from Arctic ice. We've measured trace metals in 15,000 years of ice from the Arctic, and I want to summarize that just to put the concentrations in perspective. And then the artesian flows of Springwater Township. I guess this is kind of my favorite part of the world, and there's a lot of spring water in Springwater Township. The Elmvale Groundwater Observatory is in Springwater Township. I'll show you some of my findings, and I'll talk about what I think the significance is and some of the applications. And finally, a word about apples and oranges, trace metals, concentrations for monitoring versus research purposes. So my main interest is this problem of global metal pollution. And when we study metals in the environment, it's important to remember all of the metals all have a natural source in addition to the sources from human activities. And one of my main research goals is to separate the two. So I'm interested in the effect of human activities, but I can't know that until I've quantified the natural cycle. There's approximately 70 metals in the periodic table. I'm interested in all of them. They're all fascinating. But I focus my attention on the ones that are shown here in red. Okay, there's a small group of elements that have no physiological function and are potentially toxic. So I'm most interested in silver, cadmium, mercury, thallium, lead, antimony, and arsenic. And I'll show you a few examples today of lead, which, to be honest, I've got to say, it is my favorite element. But I shouldn't say it too loud because scandium is my other favorite element, but for completely different reasons. Okay, so this is a summary of the abundance of the elements in the Earth's crust relative to silica. And the only point that I want to mention here is that these elements that I studied, lead, antimony, silver, cadmium, thallium, their concentrations in the Earth's crust is very low. That's why we call them trace elements. Okay, and the concentrations in water may be extremely low, and I'll come to that. So the concentrations that I'll be talking about today, I've organized them by category. The first one, parts per million, or milligrams per liter. In water, we think of sodium, potassium, magnesium, calcium. They're in this concentration range. And then parts per billion, which is micrograms per liter, iron and manganese, possibly copper and zinc. And then parts per trillion, I deal with this on a daily basis. This is nanograms per liter, okay? Things like silver, cadmium, lead, antimony, and thallium. And for some trace metals, on a daily basis, we deal with parts per quadrillion. Okay, and this is 10 to the minus 15 grams per gram, or picograms per liter. Okay, just a few words about water. Everybody likes water. We all need water. Here in Canada, we're very fortunate to have a lot of water in most places. It's an important part of our culture. It means more to us than even we realize. If we look at the planetary picture, yes, it's a blue planet. 97% of the water is salty, and roughly 2% is frozen. So the fresh water is only 1% of the total. And we have issues with fresh water. This is the water scarcity index. A little bit over 2 billion people are living in areas of water shortages. Okay, so there's not enough in certain parts of the world. So the quantity of water is certainly an issue. And by water, I'm talking now about fresh water resources that we drink. And there's a number of effects of human activities on our water. For example, nitrate contamination of groundwater. Biggest groundwater issue worldwide. Phosphate contamination of our surface waters. I love to go swimming in Lake Huron. I've never been swimming in Lake Erie. Phosphate contamination of surface waters is an issue. Organic contaminants. So there's a number of issues that we have because of human activities. But there's also water issues that have nothing to do with human activities. For example, the issue of arsenic in groundwater. There's probably 500 million people worldwide drinking water with elevated arsenic. It has nothing to do with contamination. It's Mother Nature. It's especially problematic in Bangladesh, where millions of people are drinking water with elevated arsenic. And there's arsenic issues in groundwater in Alberta, if you're familiar with the Beaver River, for example. Okay, the cleanest water on Earth. The cleanest water on Earth is generally considered to be ancient Arctic ice. So here we are, the Great White North. And I had an opportunity to work together with the Geological Survey of Canada, Dr. James Shang. He drilled an ice core on Devon Island. It's an ice core about 300 meters long, and it represents 15,000 years of snow accumulation. And this is the job that I just left at the University of Heidelberg in Germany. This is our clean lab for measuring trace metals. This is our sector field ICP-MS for measuring trace metals. At the lab in Heidelberg, we can measure trace metals at concentrations lower than any other lab in the world. I've moved to the University of Alberta because I have an opportunity to build an even better lab at the University of Alberta. So I was at the University of Heidelberg working on this for approximately 10 years. This is a summary of lead contamination in the Arctic of Canada during the past 150 years. So it's a logarithmic scale, and this red line here is the amount of excess lead. That's from industrial pollution. And what do we mean by excess lead? It's lead that's present in exceedance of its proportion to scandium. So we use scandium in our ice core as a reference element for what the lead concentrations should be if there was no contamination. And based on scandium, we calculate the average lead concentration in background lead, the natural amount of lead in the ice, should be 5 parts per trillion. That's our calculation. And when we measure 15,000 years of ice, the cleanest ice layers between about 4,000 and 8,000 years ago have 5 parts per trillion of lead. I want you to remember that number because I'm going to come back to this. So the cleanest water on Earth, 5 parts per trillion of lead. By the way, atmospheric lead contamination in Canada began 3,000 years ago. We see it clearly in the ice core record. To get clean water in Canada from the Arctic in the ice, we have to go back at least 4,000 years. Okay, so I wanted to put these numbers into perspective, and now I want to talk about the spring waters of Springwater Township. So Springwater Township is in Simcoe County, approximately 90 minutes north of Toronto. Don't throw anything, okay? I'm from Toronto originally, but I've been away for a long time, so it doesn't count. So Springwater Township, it got its name from the artesian springs. There's no pump here, the water's under pressure, it just flows all the time. And I've analyzed water from a number of these different artesian flows for my own scientific reasons, but also because the county had planned to build a landfill over top of one of them. And this little farm here, the Johnson Farm, it's a very special place for me because my parents bought it in 1972. So I've never lived there. I just go there every year and plant trees. But it has an artesian flow. So this is the 40th anniversary of owning this farm property. Here's the artesian flow. When I set up my first lab at the University of Bern in Switzerland, I was there for 12 years. This water was my reference water for measuring anions and cations. So it was my reference material. I've been testing this water for about 20 years now. I'm still working on it. Here's the artesian flow. It's a depth of about 13 meters, a pH of 8, lots of carbonate, alkalinity, calcium, magnesium. The water is in equilibrium with calcium carbonate. This is exactly the chemistry that we would expect for water in equilibrium with calcite and dolomite. I should mention we haven't been able to detect any tritium in the water, and I'll explain the significance of that. On the neighbor's property, we're able to measure tritium in his artesian flow. So we've collected a number of samples at different times. And when I say the neighboring farm, it's literally the next farm, and he's got tritium in his water. Okay, so tritium in the water tells us the water's not older than approximately 50 or 60 years. So I'm dealing with very recent groundwaters. I want you to remember that also. It's very young water. Site 41, the proposed landfill, there's an artesian flow beside that. Was an important test site for me, and also containing tritium. So the message that you should have here, these artesian wells contain recent groundwater. So trace metals and groundwaters. So I want to measure the trace metal chemistry of this water, but you notice here, there's a brass valve. So what's the problem with brass? Well, here's an electron micrograph of brass, and you see the lead inclusions. Brass contains a minimum of 1% lead, okay, to make it easier to machine. So if we do a time series, this is lead concentrations in parts per trillion. Parts per trillion. That first drop of water has about 5,000 parts per trillion, okay, the first drop of water. So 5 parts per billion. The drinking water guideline is 10 parts per billion. But if you let the water flow, after about 2 hours, you're down to about 20 parts per trillion. We get the same picture for all of the trace metals that we're interested in. In other words, if we have a brass valve, there's no way we can measure trace metals reliably in this water. So in 2007, we removed the brass valve. Here's the flowing water from the well. Okay, and we put on a stainless steel valve. And this was done by a colleague who just joined us at the University of Alberta, Tommy Nuremberg from Denmark, kind of a mechanical genius. Okay, and now when we do our lead analysis of the water, what's really amazing, that first drop of water, we're now down to less than 10 parts per trillion. So a huge effect of the brass valve. And this is important to me because now when I go to the farm, I'm drinking unleaded water. Okay, but we still have water coming out of galvanized steel pipes. Galvanized means it's treated with zinc, which means it contains cadmium and also lead. So that can have a positive effect on the metal concentrations in the water. This is a steel pipe I found in Heidelberg. Looks kind of ugly on the inside, but iron oxides are excellent metal filters. And if there's rust on the inside of the steel pipe, then it'll remove the metals from the water. So there's no way that we can actually use water coming out of old steel pipes. So Tommy Nuremberg also built me a bunch of really cool coring equipment using titanium. And I thought, well, let's build a titanium well. That would be really neat. Nobody's got a titanium well. It must be really clean. And I thought, on the safe side, Tommy made a couple of titanium bottles for us. And we did some leaching tests in nitric acid. And to my surprise, there's lots of lead leaching from the titanium bottles. Much more than the stainless steel. So I was really surprised and so glad we didn't invest in a titanium well. And even worse, my favorite element, scandium, is also leaching from the titanium. So titanium, not a suitable material. Okay, so we decided to go with stainless steel for our first research well. So the Elmvale Groundwater Observatory is nothing more than a couple of new wells for looking at trace metals in water. So here's the farm, okay, the original well, and this is where we've put in our 2 research wells. Here's the original well, here's our new research well in surgical stainless steel, and this one is high density polyethylene, but we cleaned it in acid before we before we installed it. So we put in 2 wells. This is a stratigraphy, so we're looking at about 13 meters of clay, which is old lake sediments, and here's our sand aquifer, and we're getting our water from here. So that's roughly what the clay and the sand look like. Okay, so this groundwater is protected by 13 meters of clay. A simplified geological cross-section. Here's the uplands. This is the source of our water. It's a moraine. And here is the old clay plain. These are glacial lake sediments, fine-grained. And there's channels of sand running under here that contain our water. I'm not a real geologist, so I consider this a cartoon explaining to you how this all works. This is us installing the plastic well. Special plastic from Denmark, cleaned in acid in Germany, and then shipped to Canada. And Tommy built that valve. Based on the hydrogeology of the site, we've located the plastic well hydrologically upstream from the steel well so that we get no contamination from the steel. And the neighbor built a little cabin. I call it the chateau. It's very small, but it houses these two wells. These are the insulated boxes so that the water doesn't freeze. The water flows all the time. The water never stops flowing. They were installed in 2009. So since they were installed, the entire volume of water has been exchanged about 40,000 times. We made a little YouTube video with the help of my youngest daughter. If you go to YouTube, Groundwater Research Wells, you can watch the water flow and listen to them also. So now your question is, well, how clean are these wells? Here's our original well, 12 ppb of iron. The stainless steel well, 8 ppb of iron. Plastic well, 4 ppb of iron. I'm not even interested in iron. The reason why I'm showing you this, even at part per billion concentrations, we see an effect of the well on our water sampling. That's my point. Okay, but my main interest is the lead, and here's our lead concentration in the plastic well versus the stainless steel. And you notice there's a lot of noise in the data. Okay, the median values are meaningless, and here's some lead concentrations of about a part per trillion. So these are extremely low concentrations, but there's a lot of noise there. And if you look at chrome, same kind of thing, about a part per trillion of chrome, with a lot of noise. So what's the source of that noise? I think it's simply the ambient air that gets incorporated in the bottle during sampling. So how clean is the air? So I had to ask Tommy to build a couple of clean air cabinets. These are laminar flow clean air cabinets with HEPA filters, okay, sliding doors so that we can now sample the water in a clean air environment. Okay, so this is me suiting up to do the water sampling in the cabin. And you can see I'm now collecting water samples within the clean air cabinet. Okay, here's Tommy with the laser particle counter. Particle counts in the ambient air, the air that we breathe. Before we collect our samples, we have 1.5 million particles larger than 0.3 microns per cubic foot of air. Okay, that's normal in a city and in a small cabin when you're walking around kicking up the dust. After sampling, we're up to 6 million particles in the air. Okay, but in our cabinets we have 0 particles, 0. So now we've eliminated the effect of the ambient air. Okay, why am I worried about ambient air? Well, lead in the atmosphere, when it's from natural sources, is mainly in the form of soil particles, right? Clay minerals, etc., etc. And larger materials like these feldspars, they're relatively large. They can be easily filtered out. The lead concentrations are low. But our lead from industrial processes is less than a micron. And that's where the lead is most highly enriched, in those aerosols. That's why I fear the effect of air on our water sampling. Because the smallest particles are the most contaminated with the trace metals we're trying to measure. So how clean is the water? Well, the first question is, how clean are my bottles? Okay, so here's lead concentrations, the plastic well, the steel well, in Teflon bottles. This data is horrible. Okay? These are clean Teflon bottles that were manufactured in a clean lab and cleaned in clean acid and were $50 each. Okay, I don't like Teflon bottles. These are our low-density polyethylene bottles from Heidelberg, and you see very high values, kind of a lot of variation. Really uncertain what the bottles are doing. The best bottles, high-density polyethylene from our plastic well. I think we're slowly getting closer to measure the concentration of lead in the water. Right now, I would say it's about a part per trillion. Okay, extremely precise data. We've eliminated the variation because of the air, and we have a nice clean bottle for lead. Okay, so lead, 1 part per trillion in our water. Thanks to James Yang, these are his bottles from the GSE that we used for the ice cores. So to put this in perspective, in the cleanest layers of ancient Arctic ice, okay, 4, 5, 6,000 years ago, we have 5 parts per trillion of lead. But in this water that's flowing right out of the ground, we have 1 part per trillion of lead. So significantly lower than the cleanest layers of ancient Arctic ice. Okay, in fact, our concentrations are comparable to ancient ice from Antarctica. And by ancient, I mean more than 2,000 years old. They're among the lowest lead concentrations ever measured at the surface of the Earth. Okay, I said the bottles are perfect for lead. So you're going to ask, we're in Alberta, we're interested in vanadium in the environment. How good are these bottles for vanadium? Well, here's vanadium concentrations, parts per trillion. Here's my low-density polyethylene bottles from the 2 different wells. And the amazing thing, we can see that the high-density polyethylene well, the plastic well, gives us significantly higher values than our stainless steel well. So the stainless steel well is cleaner for vanadium than our plastic well is. There must be traces of vanadium in that plastic. So I'm really glad we have 2 wells. Okay. Here's our high-density polyethylene bottles from the Geological Survey of Canada that are perfect for studying lead. They're absolutely horrible for vanadium. Okay, so you can see the huge difference that we have just using different bottles. So low-density polyethylene bottles, perfect for studying vanadium. High-density polyethylene, it's a disaster. Okay, so the Elmvale Groundwater Observatory, you've now heard all about it, and my idea here is I want to develop this as a reference material for measuring trace metals in water samples. Okay, so how clean is this water? We have to ask how clean is our air. We have to ask how clean are the bottles. But we also have to ask how clean are the filters. Normally when you collect a water sample, you filter it. By the way, I don't filter any of these samples. Okay, and the reason, I don't know how to filter them without contaminating them. Okay, but normally when we go out into the field, we collect a water sample and we filter it through a 0.45 micron membrane filter to get rid of the particles. That's the idea. Okay, but here's an evaluation that we did in our clean lab, various trace metals in various kinds of filters, but the cleanest filter that we can find has a blank value which exceeds the amount of lead that we have in the water. In other words, the water is so clean, we don't know how to filter it to get out the particles. And if we were to look at chrome, for example, the cleanest filter that we can get for chrome isn't clean enough when the water only contains 1 part per trillion of chrome. Okay, so we can't filter our water samples. So now you can ask me, so Bill, who cares about all this? What's the significance? Right? Trace metals in soil water. I'm interested in understanding trace metals in soil water. How much is there and why? Okay, so I go out to this area in the wintertime collecting snow samples, and I measure trace metals in the snow. That's my atmospheric input to my area. And then I measure the metals in the groundwater that comes out roughly 50 years later. And what do we find is that 99.995% 95% of the lead is being removed. So how do I know that? Well, I know what the concentration of lead must have been in southern Ontario in the 50s and the 60s when we were using leaded gasoline. It must have been at least 20 parts per billion, and now we have a part per trillion. So somehow the soil is filtering out these trace metals, and that's fascinating. And that's why I came to Alberta. That's the process I want to work on. Okay, but to work on that process, we have to have clean bottles and clean water samples. But this is one of the questions that I want to attack. This is a solubility diagram for lead carbonate at pH 8, and of course the lead concentration and equilibrium with lead carbonate will vary with the partial pressure of CO2. And this is a very standard diagram for us to try to understand the chemistry of the soil solution. But this approach, using basic chemical equilibrium thermodynamics, is not helping us to understand the concentrations of trace metal in the water, because we're dealing with concentrations orders of magnitude lower than we could get explaining with a reaction with a mineral phase. And the same thing with lead phosphate. Lead phosphate, the lead solubility will vary with phosphate concentration. Our lead concentrations are way lower than that. So to understand the chemistry of the soil and the soil solution, we have to now go back to the source of the trace metals. And we have to remind ourselves that anthropogenic emissions of trace metals to the atmosphere typically involve combustion processes, elevated temperatures, and we're generating aerosols, which are submicron particles. That's what's landing in our soil. Okay, and just to remind you of the scale, so here's some beach sand, here's a human hair, and our lead will be in aerosols much smaller than this red dot. Okay, that's what's being deposited on our soil. So the question is, how do these particles interact with our soil particles, and what's the significance then for our water? The other thing I wanted to mention here, so we've measured a long list of trace elements. So with the ICP-MS we can measure more or less everything we're interested in. And all of these trace metals that are listed here are all being filtered out by the soil. It's not that the soil's filtering out the lead, it's filtering out all of the things that you see listed here. And I think that's fascinating. The soil is doing really a remarkable job. Okay, so all of these things are depleted in the water relative to snow. But some elements, arsenic, molybdenum, tellurium, uranium, they're enriched in the water. So there's more in the water than we have in the snow, so the soil is adding arsenic and adding molybdenum and adding uranium, and also tungsten and rhenium. And this is a fascinating process also. And then our wetlands are fantastic filters for arsenic and uranium. Okay, but we don't understand how they're able to so effectively remove arsenic and uranium, and that's another process that we want to study. Okay, trace metals and surface waters. Our work has applications here. So this is my favorite lake in the world, Kawagama Lake, about 3 hours north of Toronto. It's just a beautiful lake. If we go to the middle of the lake and collect a water sample, there's only 10 parts per trillion of lead in this lake. It's only 3 hours from Toronto. It's in southern Ontario. 10 parts per trillion, that's just double the value from the ancient Arctic ice from the middle of the Holocene. So my point is here, even when we collect surface water samples, we still need to use clean lab methods for trace metal analysis. So, environmental impacts of the oil sands development. Of course, there's lots of different impacts. Well, fascinating thing about the oil sands, 190 parts per million of vanadium on average. Okay, so a 27 billion ton reserve, there's 5 million tons of vanadium in the oil sands. Okay, that's equivalent to 10% of global reserves. So if you're interested in a tracer, a metal tracer of the environmental impact of the oil sands, you could think about using vanadium. Okay, remember the high density polyethylene bottles, they are great for lead, but they're bad for vanadium. Okay, the low density polyethylene bad for lead, good for vanadium. So if we want to look at the environmental impact of the oil sands development as regards trace metals in the environment, the first question is, what bottle are we going to use? Okay, the other applications, how to sample water for trace metals, how to interpret existing data. So I think this is the last section of my presentation. I had a chance to work together with some engineers that were doing water sampling at Site 41. So this is where the Simcoe County was going to build a landfill. Okay, and at this site, they pump the water out of the well, and they let it run until it's clear, and then they filter it, and then they measure the trace metals in that water. So this is some data from our lab, but water samples from different locations at Site 41. Okay, aluminum concentrations, this is parts per billion. And you notice, first of all, within a small area, we've got this variation in aluminum concentrations and 300 parts per billion aluminum. So for those of you who've studied soil chemistry, you know that at pH 8, in equilibrium with gibbsite, you can't have 300 parts per billion of aluminum. Okay, so what's wrong with this picture? So here's the solubility diagram of gibbsite. The water has a pH of 8, which means we should have 10 to the minus, oops, I was too fast, 10 to the minus 7 moles per liter of aluminum in the water, or about 3 parts per billion. That's what we should have dissolved in the water. So how do you get 300 parts per billion? It's 100 times too much aluminum. Well, I've measured aluminum in all of these waters, from all of these flows. I never get more than 3 parts per billion. So my aluminum values are 100 times lower than the values for the monitoring well. So what's going on here? Well, if we look at their lead concentrations show the same pattern. Okay? Vanadium concentrations, it shows the same pattern. Chrome concentrations, all of these trace metals show the same pattern. Okay, they're far higher than the concentrations I'm measuring just down the road. Okay, so the values from the monitoring wells to monitor the background at the planned landfill are 1,000 times higher than what I'm measuring. But with arsenic, we see no variation. Okay, because it's anionic. So arsenic behaves differently. Molybdenum and uranium behave like arsenic. So now we see there's 2 groups of elements that are behaving differently in terms of their variation. So what is happening here? So first of all, they pump the water from the aquifer that stirs up the particles. It stirs up the sediment. It stirs up the colloids. Okay? And then they let the water run clear, so they're watching it with their eyes to determine when it's clear, and then they filter the water. And when they filter the water with a 0.45 micron membrane filter, they're removing the particles, but what about the colloids? And the colloids are those particles that are smaller than 0.45 microns and larger than a nanometer. So what I'm saying is, what they're measuring is the extent to which they've added colloids to the water during their process. Okay, they're removing the particles by filtration, and that affects the anionic and the cationic metals differently. And this is explained in this diagram. This is showing the ionic potential ionic radius. The elements in the middle, like aluminum and iron and scandium, will hydrolyze and they'll form colloids. And they're most affected by this process. And then our elements that form oxyanions will be independent of this process and remain in solution. What about the filter blanks? As I said, they filter the water samples to get rid of the particles. But if we look at the guarantee on this filter, it's guaranteed to have a blank value better than 5 parts per billion of chrome. How does this help when the chrome value in the water is orders of magnitude lower? So here's chrome concentrations in groundwater from the Ministry of Environment in Toronto for the same area. And they find about 1,000 parts per trillion. which is 1 part per billion. That's what they find. We find a part per trillion. So our data is 1,000 times lower, right? But the purpose of monitoring from the Ontario Ministry of the Environment is not to determine how much metal is in the water. The purpose is to ensure that it doesn't exceed the drinking water guideline for that element. It's a completely different purpose. And that's what we have to realize when we look at data from the Ministry of the Environment. Okay? So reported concentrations from monitoring studies, we have to take those concentrations and interpret them with great care. Okay, the Health Canada guideline is 50 parts per billion for chrome. So you could say, Bill, what's the point of knowing if it's 1 part per trillion or 2 parts per trillion, if the drinking water guideline is so much higher? I just want to mention that the California EPA is considering a new public health goal for hexavalent chromium of 60 parts per trillion. Okay? And so then it becomes relevant what's actually in the water. So measuring trace metal concentrations in water. So to summarize what I've put together for you, there is a difference between monitoring and research. And to be honest, it's like apples and oranges. Okay, 2 completely different purposes. I'm trying to measure what's in the water and to find out why. The Ministry of the Environment just needs to ensure it doesn't exceed the drinking water guideline. So, apples and oranges, we've always been told they're very different, right? Here's the infrared spectrum. They're very similar, okay? You just have to be careful when you make comparisons. That's my message. So to summarize, the concentrations of many potentially toxic trace metals in surface waters and groundwaters and spring waters may be at or below the levels found in ancient Arctic ice. How many labs in the world can measure trace metals in ancient Arctic ice? Arguably, there are 3 labs in the world that do that work. Okay? Most people don't realize the water coming out of the ground from our soil can be even cleaner than that. Okay, the analytical sensitivity, we need to use sector field ICP-MS. That's that large ICP-MS I showed you at the beginning, which has tremendous sensitivity. Okay, we can measure orders of magnitude lower than what you see here. And then you need to use clean lab methods. Clean air, clean containers, clean reagents, clean clothing, clean bottles. You have to be a little bit of a fanatic. Thanks very much for your attention.
Thanks, Bill. We have time for some questions for Bill, and then we'll open it up to questions for any of the speakers from this morning.
Is that landfill still going? Are they going to go ahead with it, or?
I'm very happy to announce it's a good news story. While I was doing all of this work in my spare time, I started an annual water festival called the Elmvale Water Festival, which is named after that village. And I created a foundation for environmental education, the Elmvale Foundation, to raise awareness about the importance of good, clean water. And we had some awesome speakers from across Canada, including some from Alberta. And a lot of people got on board to help the community trying to stop the landfill. And at the end of the day, it was all shut down, and that land has been reverted back to agriculture.
Why is there high levels of arsenic in fruit juice?
High levels of arsenic in?
High levels of arsenic in fruit juice.
In fruit juice?
That could be great, but they do use arsenic sometimes in the orchard, but not yet, probably anymore.
There's a bunch of possible sources, a lot of different possible sources. Oh, thank you. A lot lot of possible sources. The first one that I would start with would be the water. I mean, it's common that arsenic is naturally elevated in the water. It's often removed during processing. I mean, this has been an issue for the water bottling companies, as you can imagine. So the first thing to look at is the water, and then the soil in the area. I mean, some of the traditional pesticides contained arsenic, lead and arsenic, et cetera, so leaching out of the soil. And then the other possibility, depending on the levels that you're talking about, would be packaging. So we've studied bottled waters from around the world. They're all contaminated. The bottled waters in PET plastic are contaminated with antimony, which leaches out of the plastic. And the bottled waters in glass are contaminated with lead, which leaches out of the glass, but sometimes we see arsenic leaching out of the glass also. So that could be another possible source at low levels, depending on the pH and storage time. Scott?
Yeah, I was fascinated to see that you made your cabinet was so effective. In the role the particles, if you elaborate on the mechanism, show them, and how did that appear to remove the micro-size particles?
Yeah, so the way the filters work, those are high efficiency particle filters. So they're pretty standard in any sort of clean lab environment. And they remove, I think, 99.9999% of the particles larger than a half a micron. So those clean air cabinets, I should mention James Zhang at the Geological Survey, the Ice Core guy, he designed the clean air cabinets, and then Tommy Nuremberg built them. But Scott, I can also tell you, given our very limited budget with these studies, these are homemade clean air cabinets. We have an amazing clean lab in Heidelberg, and those clean air cabinets, I think, were about 60,000 euros each. They were the best clean air cabinets you could imagine. But those little clean air cabinets in Elmvale, I've never seen such clean air before. They're really amazing. Yes? Yeah, that's a really great question. In fact, I'm really glad that you asked that, because I wanted to talk about that. So Kawagama Lake, if you send me an email, I'll send you the publication. But Kawagama Lake, I mentioned that that's my favorite lake in the world, so I spent a couple of summers, we were there on family vacation, but I went around collecting the stream water samples, and it's really fascinating. If you look at the streams coming into the lake, you're looking at up to 1,000 parts per trillion of lead, or 1 part per billion of lead, in the streams coming into the lake. But if you go out into the middle of the lake, you're down to 10 parts per trillion, okay, and sometimes less than that. But what I didn't have time for today, we not only measure the lead concentrations, we measure the lead isotope ratios. So we can distinguish between industrial lead and natural lead. So if you look at the isotope ratios of the lead that comes in the stream, much higher concentrations, but that fingerprint is a completely different signature, and it looks more like, well, it has a stronger influence of the rocks in the area. Okay, so the rocks in the area, 1.4 billion years old, they have a certain lead isotope fingerprint based on their age. So you see in the stream water coming in, high lead and more influenced by that natural value, and then in the middle of the lake, it's a completely different fingerprint. It's not only well removed from the natural value, it's well removed from gasoline lead, which is the value that we expected, but it matches the lead isotope ratios for the base metal sulfide ores in Sudbury, and also the lead smelter in northern Quebec. So in the middle of the lake, it's actually more of a signature that we're getting from atmospheric deposition from northern Ontario and Quebec. So your question is a very good one. There's a 100-time difference in lead concentration going from the stream to the middle of the lake. And this is why I would be very careful interpreting any data on trace metals in surface waters unless you've taken exactly that into account. The more velocity that you have, the more particles that you have, the higher the concentrations are going to be. Okay, and the way Mother Nature works, once that water goes into the lake, it has less energy, and those particles will begin to settle, and then you'll have much lower concentrations in the water. So a lot of variation.
Sorry, I was just wondering, how did you address the air concentration of lead in those ice cores? Did you separate those air concentrations?
Yeah, that's a good question. So working with the ice cores, it's a huge amount of work, okay? So it costs about $500,000 to collect one core. And James not only did all the work I showed you here, but he developed a titanium core, okay? So that when you collect an ice core with his new corer, the outside of the ice core is much less contaminated than it would have been if you used a conventional core. But even with this clean ice core, the outside of the ice core is contaminated with lead. So what James does, he ships all the ice cores to Ottawa, and he built his own clean lab, but it's minus 18 degrees. And inside that clean lab, he then has a mechanical lathe, and he'll mechanically remove the outside layers of the ice, okay, and it's the inside part of the ice that gets melted and then brought to Heidelberg to measure. So that's a very good question. If you look at the old data on metals and ice cores, it's all rubbish, just because they haven't considered that. And those authors will tell you that the data is rubbish.
Sorry, but what happened to the ice, air trapped in those ice? Like, is there any information like what was the concentration of lead in the air in those period?
Well, yeah. So with the lead story here, I've only showed the parts of it to explain how clean the old ice layers are. Okay, so if you send me an email, I can send you all those publications. So there's a detailed reconstruction of lead pollution history. So we see the lead pollution beginning 3,000 years ago with the Phoenicians trading in Spain, and then that goes into decline, and then the Roman lead 2,000 years ago, and that goes into decline, and then the German lead mining in the medieval period 1,000 years ago, and so that's all preserved in those ice cores. It's an amazing history.
Can I diverge a little bit? The last few days, the science media have been carrying an awful lot of information about the Russians having completed their 20-year core hole 2 miles deep into an active lake in Antarctica. Those 20 years of coring, have those ice core samples the information from all that 12,000 feet of ice that they've been available as to how much change occurred over that time period?
You're asking now for changes in metals or sort of climate change, etc.?
Just generally. I mean, that's probably one of the oldest collection, longest time period of collection ice cores to the deepest depth.
Right, right. So I haven't followed the story with the ice cores. So I mean, I know Thomas Stocker in Bern, and he's done the CO2 and the methane and the Antarctic ice. And some of the people in Heidelberg have been doing the beryllium-10, et cetera, et cetera. But I've only followed that story back 600,000 years. Sort of the variation in the CO2 and methane. So, you know, the latest on all of that, I'm not familiar with it. I think they were hoping for 1.5 million years of ice. I think that was the hope. So this ice core that we've been looking at for the metals is really young in comparison.
Yeah, I was just wondering whether the information that was being collected with every year's coring was being made available or whether there's
Well, having spent all those years in Europe, I can tell you that only certain people get access to those ice cores. Only certain people get access to those ice cores. And if you wanted to do something in it, then you've got to be part of that group, that's for sure. Was that diplomatically correct?
Well, that's all the time we have for questions exclusively for Bill. So let's give him another round of applause.